DB2 optimizer development. And a lot of you may think that optimizer development and R are not really close topics together. But I've done a lot of work with R personally, and so I thought there's some unique information here for you. And this is, I don't know if any of you guys attended my talk last year on R, but this is a continuation, a much more in-depth example on how to integrate R into a SQL workflow as opposed to driving R just as R and using the data as a provider. Now, how many people here actually use R? So you actually do have some experience with it. How do you normally do your analysis with it? Do you run it through RStudio? Do you have some other scripts that you run? How's it done? RStudio? Yeah. That's a very common way of doing it. It's an easy paradigm to understand. So today, my objectives are to explain to you why an integrated SQL R workflow can be superior to a workflow driven just from R, like RStudio or the R command line or any other strict R-driven approach. I'm going to show you how to improve your analytics by combining DB2 with R, and I want to demonstrate for you a method for driving R analysis directly from your SQL queries. Now, as an overview of what I'm actually going to talk about, this is based on a real-world example, so I'm going to give you an overview of the data. I'm going to contrast R and SQL-driven analysis. I'm going to review the functions from last year. Now, did any of you attend my talk last year? Okay, a couple of people did. But so yeah, I'm going to go over this basic infrastructure for invoking R within DB2 SQL, and then this goes into the real example of the multi-stage analysis driving R through SQL. And then I'm going to spend just a couple minutes on talking about our integration into dashDB, which is our cloud-based product. So this example all stems from solar analysis. At home, I have 41 solar panels on my roof. They came online in 2011, and the goal is to compare panel performance, because what you may not know about solar panels is they degrade approximately 0.5% per year. And so when this system came online and I was talking to the installer about it, and I'm saying, so how do I know if these panels are performing? And he kind of said, well, you can kind of look at the online monitoring graphs that we show, and you can pick out a good day here, and you can kind of manually search back over years of data to try and find something that looks the same. And if you see there's a drastic difference in performance, then maybe you should call us. And now I'm a database developer, and I thought about this, and I said, this is a totally stupid way of measuring panel performance, right? Yeah, I can see the graphs. I can see that today on average it produced, this much power, but really his method tells me nothing. Tells me absolutely nothing about how things are performing. So this is what gave rise to this presentation and to the methodology that I've developed. And as a SQL optimizer developer, I really do think SQL is the best way of driving any kind of analysis. It's repeatable, it allows you to store it, allows you to take advantage of database functionality. So, and since I love SQL, what did I do? I figured out a way to do this, and that's what I'm here today to show you. So, solar analysis is challenging on its own. There's a lot of problems with it. We have shading issues, we have cloud cover issues. The sun is in a different position throughout the year. I live in Canada, so in the winter we get like 10 hours of sunlight. In the summer we get like 18. Not quite that bad, but there's quite a variety of solar exposure to our panels. The temperature affects the panels. So in the summer when it's stinking hot and humid, the panels aren't actually performing as efficiently as they are in April. It's really kind of strange, but that's what it is. And the second issue is the volume of data. From my data provider, I get approximately 1,500 data points per panel per day. That's 110 million data points right now, and this is for 41 panels. It's approximately 10 gigs of data over 5 years. So if you're looking at a commercial solar farm, you're easily into the hundreds of gigs or terabytes of data over a very quick period of time. And you can't do that analysis manually. It's just too much. And the data itself that I have, it's all in CSV files, right? This is what I download. And it would be nice if in an ideal world they'd be delineated per panel, per day, but they're commingled, right? My data provider went down for 6 months, so I've got one huge CSV file that has 6 months worth of data for, every panel, every day, every 1,500 points per day, whatever that is, every 2 seconds. So it's a big volume of data. It's really too big to analyze in a manual fashion. And just as an example, so here are 4 pictures of solar profiles. Now, if I'm looking at that top profile, which one is best to compare with? Come on, this is an easy question. Someone. Which one? The top one is my target. So which one of these 3 is best to compare with? The lower left, of course. It's obviously that one. One is April 20th, 2016. One is April 18th, 2015. And they're actually a pretty close match. One is 51.14 kilowatt hours, and the other one is 52.06 kilowatt hours. So it's actually a very reasonable comparison. Visually, we can look at that and we can say, oh yeah, they're close. They've got a nice smooth curve. They've got that one kind of null value where the data in transit got dropped. Right, but overall they look very similar, and the aggregate statistics tells you that it is, in fact, a very comparable thing. Now these are 1 year and 2 days apart. The time difference could be even greater. If I had several weeks of scattered cloudiness, I might not get a nice smooth profile like that. Or if there's a high amount of dust or pollen in the air, if I haven't had rain for several weeks and stuff is actually starting to settle out on the panels, it can all affect the production curve. So for example, here's another profile. It's not nearly as smooth. It's still pretty close. It's 49.48 kilowatt hours. It's from 2 weeks before, April 9th, 2016. It's still a good day for comparison, but I couldn't directly compare this curve with the very nice smooth curves from the day before. Doesn't work. There's too much spikiness in the data. And so what we've got here is a problem. We need to find a method of getting data that is worth comparing. I can't compare just exactly with April 9th, 2015 or 2014 or 2011 because I might get this. I might get the really low curves from the prior that I showed on the prior slides. So I have to search over a range of data, and I have to account for things like the solar exposure, how much sun is actually hitting the panels, and I don't have that data personally. I don't have a dedicated irradiance monitor. I only have the information produced by my solar panels. So as I was saying, we have to search over a range of data in prior years. For my purpose, I look at a short time window. So if I'm looking at a production curve from April 19th, 2016, I might choose plus or minus a week in 2015, 2014, etc., to kind of time box the position of the sun in the sky so that it's at least quite similar. And so I need to search for these compatible days in the prior years. And as I said, I don't have cloud cover data, I don't have weather data, and even the weather station 10 kilometers away does not necessarily get the same cloud cover that I do at my home. So we have to infer what can be compared just from the limited data produced by the panels themselves. So the overall methodology for this analysis is for each panel and day, we're going to build a production profile of that panel, and then we're going to use that to compare to other panels in the current month and to prior years. And now the panels, there are certain production profiles of interest, those with maximum production or a very smooth curve, and this we can all tell from the analysis data. And a comparison of the current profile in prior years will then tell us whether the panels are operating as expected. So, now you all said earlier that, or a number of you said that you do use R and you've driven it typically through RStudio. And RStudio is a great tool. It's a very efficient way for developing R code. It's an easy paradigm to understand. Load my data in, do my stuff on it, learn what I need to learn, and then I'm finished. It's great. You can save the script so it becomes repeatable. You can invoke things in different ways. You can build plots. It's a very good tool. I quite like it. It's a good tool for data exploration. I don't think it's a good tool for large-scale analysis over a long period of time. as I said, this is 110 million data points. I don't want to load CSV files for 110 million data points directly into RStudio, even if RStudio's memory could handle that much data. Yeah, and so in that system, if I was doing this directly in R or RStudio, I may choose a production profile for April 19th, and I may go and compare, and I got to do some calculation on data from prior years, and then, okay, next month I've got my June data now, or my May data, and I'm doing it again, and I got to go recompute that data. But I already did that computation last year, and maybe the year before, or, so there can be significant recomputation over large data sets. Now, the advantage of a database-driven analysis, and I already spoke on this a little bit, but there are some problems that are more naturally driven from a database. When there are significant operations that can be performed in your database, when the analysis can be modularized into working on small subsets of this huge data set that the database can more easily find and give to you. If I want to combine the intermediate analysis results with new raw data or other analytic results, and if I want the output of my analysis to be consumable in some fashion, do you know of a reporting tool that understands our output directly? I don't. Cognos and other BI tools, they understand SQL. They understand, DRDA communications, right? So if you want something to be consumable and repeatable and operate over large data, a database-driven approach is really what I think is the best way. So in a database-driven approach, we can combine R scripts, multiple stages of our analysis using normal SQL operations, joins, unions, etc. Post-analysis operations such as aggregations can occur within DB2 or really any other database, but this is focused on DB2, where you've got more memory, optimized algorithms. The result of one script can be used as input to many ones. And the large data sets don't actually need to flow to the client. I don't need to flow 10 gigs of data from my database over the client connection to my local ThinkPad or to my department server. It all stays on the server, it's done on the server, and all you're getting back at the end is the actual result of your analysis. And even on the server, you can do things that you wouldn't think of. You can generate plots. A lot of data analysis generates graphical plots, so you can visualize what you're seeing, and it's a really great thing to have in your report. Well, that can be done on the server as easily on the client. You just have to get the data off. And that can be done via SQL as well. So, and now why this particular analysis did I look at for SQL? And I already said mainly because I love SQL and I think it's the best way to do things. But going back to what I thought would be a good thing for a database-driven analysis, I've got a lot of data to process. I've got a lot of different steps, and I'm really looking at small slices of that, of gaining insight about individual slices of that data, each panel each day, or each panel in a given month. So it's a really good way to just do that little portion of the analysis. So that's why this analysis lends itself to a SQL-driven approach. And the moving window, as I mentioned, for days within a certain time box period in prior years, that's also easily expressed within SQL. So since most of you have not seen my presentation from last year, I'm going to do a very quick review of actually the nuts and bolts of integrating R into SQL. And this is really done through user-defined functions, just as you would do any kind of other external code. So this function, it's self-describing. It does not enforce a tie between the R script and the database. So you can develop your script in RStudio, and you can plug it into the database. The only thing you have to change is, of course, where you're getting your data. When you developed in RStudio, you probably loaded it from a CSV file, or you used a SQL query to pull it into a data frame. So that part has to change. But the actual analysis steps, the variable names, all of those don't have to change. It gives you a dynamic R script, and it can provide one or more output values back to DB2. And in this particular case and in this particular implementation, it is implicitly handling group-based analysis instead of just a row at a time ranking. Most people think of functions and they think, oh, okay, get a data, provide me a rank. Well, this is not doing that. This is providing more of an aggregation level of analysis. And you can even do more than that. You don't have to limit yourself to just aggregation. So the building blocks of any UDF in DB2 is you need your compilers, of course. You need whatever the underlying libraries are. You need the R package. You need a couple of add-ons, RCPP and RInside are the big ones. And any additional libraries that your actual analysis requires. Things like ggplot2 or minpaclm. These are all external libraries that, of course, have to be installed in the database server onto each node of your cluster, if it's a DPF environment. But it's these are kind of administrative things that are not hugely difficult. And it's pretty clear what needs to be done. And with anything else, yes. Does that mean root, or can you do it as instance? You can actually do it as instance owner. On my little laptop here, I have a Linux VM running DB2 10.5 FixPack 5. I have R installed in there. I have it installed. I have one user ID where it's just installed as the local user ID. So all the individual R libraries. So R itself is installed by root as a system package. All the add-on libraries, RInside, RCPP, minpaclm, all these things were just installed as the local instance owner. I didn't have to get root to install those. And they work because the library paths are still accessible. And of course, with any good software architecture and deployment system, you need development and test. You need a test environment so you can test this. One of the poor things about external UDFs, and especially with R, is your error messages are limited. You've got 70 characters to return from the R UDF when an error occurs in the script. So unfortunately, it's not a lot. So you do need a development and test environment where you can easily build and you can test things out to make sure your script is doing what it's supposed to do and not affecting your production system. So this example is really based on RInside and RCPP. I'm a C++ developer myself. I can do Java if I have to, but I'm much more comfortable in RInside or in C++. So RInside and RCPP are two base packages that provide the C++ integration into R. JRI is a very similar package for Java, if that's your preference. It'll work just as well. The links for where to get these packages are there, or there's just a very simple install command, install.packages RInside and install.packages RCPP, and they're going to be right there for you. Now, as an external function, of course, we have to have this function cataloged in our database. And so this is an example of a simplified create function statement that is going to be used in this example. I say simplified because it's only got two input variables and it only returns a single scalar value. I had to simplify this down from the real example so that it actually fit on a small number of slides, because otherwise it would be, I'd spend lots of time going through it. So the notable things about this kind of script is I'm passing in names, name 1 and name 2. And these are actual names for the variables in the R script. I don't have to create a convention that says, thou shalt name your variable P1 and P2 and P3. The data scientists can develop their script in whatever way they want. They can name the variables whatever they want, and we're just using this in the SQL to tell it to them. And so here I'm taking in two numeric variables with name 1 and name 2. I'm taking in the row and the group count. So as I said, this is kind of an aggregation example. So the ordinal value of the row within the group, so the ordinal value of the solar panel reading within the particular panels for that day, and the group, how many rows are actually in the group, so that I know when I've got all the rows, so that I can actually do the full aggregation analysis. And it also takes in a variable script that you can provide as a constant, a parameter marker, anything you would like. And then there's just some other normal DB2 function keywords there. It is deterministic. We're going to run it in a fenced environment because this is, after all, external code to DB2, and we don't want some memory error to bring down your DB2 instance. I'm going to say it's not thread safe so that if I'm running concurrent copies of R, they're not potentially, or concurrent SQL with R UDFs, that they are not going to interfere with one another, so they're all running in their own DB2 fenced process. We need a Scratchpad, we need a final call, and this does not actually involve SQL at all internally to R. So as a Scratchpad, we have to store, of course, our numeric vectors in our R instance, so a very simple Scratchpad definition. Of course, as you get more parameters, this will grow, and you may need to specify a larger size for the Scratchpad, but this is sufficient here. And then here's your actual C++ function definition. And I know it looks large, but it follows the same pattern. The numerical value of the name, the numerical value of the name, the row num, the group count, the script, and then our output value, which in this case is a double, and then all our null indicators. So, and then here we actually have a UDF body. The first call here, this happens at the very first call of the UDF. We have to initialize the Scratchpad, we have to initialize our numeric vectors, and we have to start up the R instance. And in a scalar UDF, for this we fall through to the normal case, which is then where we actually do the real work. For most calls, we're just pushing the numerical input parameters into our variables that are on our Scratchpad. When we hit the group boundary, here we are assigning the numeric list to a name in R. And this name is provided, so it matches the name that was given in by the data scientist in the script. And we're doing the same thing for name 2. And then here, we're just calling the script and getting back our output number. Now in this example, as an aggregation example, we're only invoking R when we hit that group boundary. But you don't have to do that. I mean, you can invoke R for every single row if you want to do some kind of intermediate calculation. R is persistent between calls. So your variables will persist in R. Whatever calculations you're doing will persist. They will be there. So you could do this for every single row if you needed to. In this example, since it's aggregation, I'm only doing it at the last group boundary. And here I'm doing it as a scalar UDF, so it's only returning a single value. So that's why it's using this particular syntax. In the real example that you will find in the detailed slides, you can see it's using a table function UDF, where it is extracting multiple values out of the R script to return. And all those examples are in the PDF that you can download for this presentation. It goes on for pages and pages. It has all sorts of error handling and exception handling and type checking and all the good stuff that you'd really want in a production example. And then the last part of any UDF like this is the final call, where we're going to clean up our memory in the fenced process, and then we're finished. And then here's an example of actually calling this. This inner subselect is providing the input data. So here we've got some interesting parameters. This is our row number within the group, and as this is an aggregation, we're partitioning by sample date and vBoost ID, which is essentially the particular panel. And we're also grabbing the count for the group. And because I don't really want to have to deal with the null values, I'm making sure that our input data is not null. And I'm using max at the end here, just in case the final analysis result is going to return null. If the calculation couldn't be completed, or if there was an error and you chose just to pass that error on, then you'll get a null value out, and I may not want to see that in my final report result. Maybe I will. It's really up to you. The max is especially useful in DPF if you're doing this to ensure that the data stays partitioned during the R invocation, that we're not going to start TQing the data in random ways. And in particular with that, you will notice that the group by clause is the same as the partition by clause. And that helps us to ensure data stays partitioned the way we want. Coming in version 11, we actually have user-defined aggregate functions, so we don't have to use tricks like this. But again, that will only be sufficient then for aggregates, not for any row at a time that you want to process. So the R function provides the generic interface, and as I said, to fit on a couple of slides, it's only taking 2 variables. And they don't have to be literals. They could be parameter markers. They could be whatever you'd like. So now I'm going to talk about how to actually integrate this into a real SQL-driven analysis. And so just to recap, what we want to do today is we want to build the profile per panel per day. We want to determine which panels are of interest in the current month or the current year. And for those panels, we want to find the panels in prior years that are similar so that we can then do a more detailed comparison on those panels. And that will show us whether the panels are operating as expected. So as an outline of what a production profile is, in this scatter plot here, each of the individual dots represents the original data points. And so when I'm building a production profile, I'm trying to build a smooth curve that closely fits to those points. Now this is a nonlinear regression model based on the data points itself, and that profile, those, I think it's 6 parameters that are output from that profile, are what I use for the main comparison throughout this analysis. And when the profile is close enough for different days, then we can actually say these are close. Let's go back to the base data points to do the real detailed comparison. So the stage 1 analysis, it's got a couple of input variables, the epoch, which is the number of seconds since 4 a.m., and the pout, which is the output power of a given panel. And I've calculated all of this in SQL. So here's calculating our epoch, which is the date plus 4 hours, or the time of the sample minus the date plus 4 hours. And I say 4 hours because I want to start at 4 a.m. Production really doesn't ramp up in our area of the world until about 4:35. So this provides a good base. I already showed the grouping information that was here, and this predicate here is just because, let's say, this is the data I just ingested, so this is what I'm focused on this month. And so this is just building our input data to R. This is a relatively simple regression model with only two dependent variables. And so then this next step is the actual invocation of R. And so here we've got our source epoch and the name in the script, and our power out and the name in the script. And you'll notice that these names are case sensitive because R is case sensitive. So if I replace this with the lowercase p and then try and run this script, it's going to give an error because we need to pass in the sensitive names. So if you're ever using a SQL formatter or anything, be careful that it doesn't change the case on you because that takes a long time to figure out because it's such a minor change in the script. And I've stored all my scripts for this in a particular table, so I'm just looking up that script by name. It's been saved there. It's, as a database table, it is under whatever security authorities you want to provide. So if you're going to have a very restrictive review process that no one can insert into this until it's gone through, umpteen levels of check marks, then you can do that. And that way you as a DBA or as an application developer, you know what's going to be running in there and people can't change it ad hoc. You could provide it as a parameter marker from the application if you wanted, or you could provide it as a constant in the query, although that gets pretty large, or any other method you could think of. I mean, this could be a library with just a function call. Really, it's up to you. And so then again, in the real example, this is a table function. So here we have our output parameters, which are the result of the fitting. And again, those names are case sensitive. And because, I'm thinking that an application developer and the data scientist may not talk so well to one another, he may use wonderful names like these, and the application developer says, well, I really don't want that. I want more meaningful names. Centered, height 1, height 2, things of that nature. So you can rename the output variables from the R script in SQL. And then this is actually the simple script for this first part of the data. Again, here we have our 2 input variables. They're vectors. And at the point this is invoked, they will each contain approximately 1,500 values. We're creating a data frame from them. We're fitting this linear regression model. It's based on a Gaussian, but it's also got a quadratic portion to it with our data. And then here we are pulling out the various output parameters we want. These are the curve fitting parameters. This is the residual sum of squares, which is an error check. And then these two are the actual production from the data and the estimated production from the fitted curve and the actual production from the data. So that's what these variables are. And again, this is just to show you pulling out the particular pieces into independent variables so that you can return them at the group boundary. Is there any questions before I go on beyond this? Because I know this is a pretty detailed technical stuff so far. No? Okay. I'm glad it's good and well understood. So, and then this here is just an example SQL putting it all together. I want to save the data because I'm going to use it multiple times. I'm going to insert it into another table in DB2. Here is our input data. Here is our function execution. And here I just am saying, well, if the calculation didn't result anything, then I don't actually want that information for that group. And so this is one SQL statement. It is building the data. It is driving an R analysis. It is storing in another table to use later. So the second part of our analysis was finding the panels or the days of interest, ones that had maximal production or a very smooth curve. And this is an example SQL query. And really it's just saying if the actual production is within 2% of the maximum production, then that's something we want to consider more. And that's really all it's saying, despite being, having some complex expressions to calculate our percentages. And again, it's for this period of interest because that's the data I just ingested into the database and I'm working on my analysis. And this is just the table that I populated in the prior step. So after we found the days of interest, we want to ensure in the current month or in that day that all the panels are performing approximately the same. I mean, part of the analysis is going back prior years, but I also want to find out that the panels are operating all the same. I want to find out if a panel has somehow malfunctioned and shut down or if there's some other issue. So for this step, I'm going to compare the individual production profiles in the current day. And from the residuals, you will see that there's an error, although I don't show it here. I also plot the production curves because that's a more easier method for seeing the difference, for this presentation. So briefly, it's choosing the target profile and then comparing the data. The full SQL is again shown in the appendices of the presentation you can download. For this here, I'm only going to show a few snippets. So here we have our data that I described in step 2, the panels of interest. And here is just a local, here is another data set. This is our curve data. We're pulling data out of the previously saved data and out of our dates of interest. And we're picking the median date or the median curve for that date. So this is already based on panels that had days that had maximum performance. And now we're just taking the middle panel of that day to use as a comparison for the others. Here's a simple R script just to compute the residuals again. It's using the curve parameters from the median chosen earlier in the day, and again back to the original data points to compute the residuals. So what it means is that the smaller residuals at output will tell you that this is a pretty close match to our target, which just happened to be the median panel. And so then based on those calculations, we're going to generate plot images for these panels as well as return the actual residuals that you might use in a report or subsequent SQL steps. Now I use ggplot2 as a graphics library because it's very powerful. It's got a useful interface. The files generated by ggplot2, you could save them on the server, return them, just return a path to them so you can get them over NFS or some other system, or you could read the UDF into a blob and actually return the blob as part of the SQL data stream. It's really up to you. So here we go. Here's just an example, a script of generating this plot data. Here we've gone through. I don't know how many people are familiar with ggplot2, but here we've created our curve. Here we've created a little bit of sample data based on the curve, and then here we're plotting it. And so in the end, I get a curve like this. And this is for April 19th, 2016. This was a day that had good overall production, but you can see there's some issues here. And this showed up in the residuals as well, although looking at a table of 41 real numbers in a presentation is not really going to be insightful to you. This is far more insightful. These dips are most likely due to shading or dirt on the panels. I haven't had time to actually go back and check why we have these new dips here this April. But you can tell quite clearly that something is going wrong because they shouldn't all be dropping off like that, or 9 of them shouldn't be dropping off like that. I do. I have an 18-foot. Yeah. Oh, yeah. Yeah. No, I have an 18-foot pressure washer wand, so I can stand above the roof and go to wash them. But yeah. No, I will definitely keep a note of when I wash them, so that I can then go and compare a good day after that to the good day before that, so that because it is most likely dirt on the panels, pollen and dust. That's most likely why. To be honest, it's unlikely to be an equipment malfunction, but it's possible. Pardon? They don't have a lifespan. I mean, they will continue producing forever. By 25, 30 years from now, their production will be down to a point that you may want to consider replacing them. So they don't really have a defined lifespan. I mean, panels are silicone, a little bit of boron, glass, and aluminum, and wires. So there's not a lot of no moving components. It's just electrons flowing. Other system components. So panel warranties are based on production. So the company warrants that in 20 years your panels will still be producing at 90% of what they were when you bought them. But how do I measure it? That's the whole basis of this presentation. How do I measure that now after 5 years they're still producing within 97.5% of what they did originally? So, yep. Was there another question? Okay. So the next stage in the analysis is actually to go and compare with prior years. And it's going to be very similar to what we did for the current day. We've picked our panels of interest in April, and now we're going to start searching back through time to find panels within a short time-boxed window that have similar production profiles, so that we can actually start comparing the residuals and the data points to say that, yes, this is within 2% or not. And of course, because we saw that bad data, for April 19th, we're going to have to take that into account as well in prior years, because all of a sudden prior years are hopefully going to have a much higher production than those panels are this year. And as I outlined, we can't compare to the same day, because the same day may be cloudy. It may be covered in pollen. We don't know. And this kind of finding of similar panels in a time box period is something that can easily be expressed in SQL. Easily for me. Probably easy for you. How would you express this in a native R script that you're loading from CSV files? Well, you've got to have some kind of array that tells you which file contains which range of data, and you've got to go and you've got to load that file, and you've got to pick out pieces of that file. If one of my files contains 6 months worth of data, that's a huge chunk of data. The database can do that all for me. It can do it easily. It can use indexes. It can use good SQL constructs. So, I mean, again, here is our data described under step 2, which is really the dates of interest. In this particular case, there was 3. There was April 20th, April 19th, and April 9th in this. And so here we're going through and we're looking at the prior year's data. And this is our prior year's curve data. And to fit this on one slide, I specifically specified a range in 2014 and 2015. The example SQL in the appendix actually shows doing this dynamically using SQL to pick out the range of dates of interest without specifying constants. And again here I'm saying I want it within 1 year plus or minus 1 week. and again our curve parameters, within 2% of the target curve, within plus or minus 1 week. So that's what it is. And so the entire analysis has been based on this combination of pre-done computations with the original data set combined with our existing analytic data. In my view, it fits very well with a SQL-driven analysis, and it is shifting work to the database engine. It is shifting the work of finding relevant rows. It is shifting aggregation work. It is shifting the windowing work into the database so that I don't have to worry about any of that in R. And that's where I think the real power of doing this kind of analysis is. And it's also helping keep your script simpler. I mean, you saw several examples of script. One of them was 2 lines, one of them was 5 lines, right? Because they can really focus on just a single data frame, as if I have everything there that I need. I don't need to do any filtering because the database has done it for me. I don't need to pull out certain pieces because it's all already been done. And it uses one single UDF for all of these analysis steps. There's one single generic UDF that I've created. I think it contains 10 input values, a mix of numerics, integers, and strings, and it gives the 8 output numerics in one string, but it is used for every single invocation in this. And I could continue with pages and pages of SQL and R scripting, and if you go through the appendix, you will see pages and pages of it, but I hope that my point is clear, because I imagine the SQL is getting pretty unintelligible, at least on a slide deck. So this is the end of what I'm going to talk about for in-database SQL-driven analysis. So this is a really good time for questions or discussions about the methods I've discussed there. And then after this, I'll go into dashDB and Bluemix. So anything? No? Okay. All right. So dashDB and Bluemix, it has enhancements to allow in-database analytics in a very similar way. We support both in-database analytics, which is what I've shown you here, and we support in-application analytics. Bluemix has a built-in R instance that already has all the, a built-in instance of RStudio, which already has all the connections to your dashDB database, so that you can just use it as a data source for in application analytics, or you can use it for in-database analytics, which is what I've shown here. To be consistent with the R paradigm, since we have RStudio right there, most people choose to use to drive their analytics through RStudio, because that's a natural paradigm for many data scientists. So they like that, they're familiar with that. So that is still there. And under the covers, though, it drives the SQL queries that actually push the analytics into the database itself, in a similar method to what I've done here, except it kind of hides it from you. So yes, in applications, we typically operate on DataFrames. They contain actual data. Bluemix, instead, it uses an IDA frame, which is really just a pointer to a table, a view, a SQL statement that provides the source of your data. And so that IDA data frame doesn't do computations in the RStudio instance. It does it down in the Bluemix engine, in the dashDB engine. And as I said, it's been driven from RStudio in Bluemix. And our IBM Knowledge Center contains many useful examples of actually doing this through dashDB and Bluemix. So please go through that. And of course, you can register for Bluemix there and give it a try. And all the examples that I have are in the appendices of this presentation. The UDF source code, the routines to actually build it and install it into your SQL lib, all the various R scripts, all the various SQL scripts. Of course, you can't use them because you don't have my data, but it will at least provide you an example for you to build your own example, your own test bed, and prove to yourself that this is a useful methodology. So that's all I have for the presentation. I guess I expected a few more questions. So. No, I don't. I've never thought about putting it up there. It's also 10 gigs worth of data, so it's a lot. Yeah, no, I could put up. I could probably put up a month from like April from this year and April from last year. Take my card and email me. My card is beside the projector there, and send me an email about that, and I can make some data available to you. Aside from those 9 panels that have those weird dips, yeah. The rest of the system is producing well. It is actually it's showing almost no degradation from 2014 and 2013. Since 2011, there's been approximately 0.5%. So that's well within the power warranty, and aside from this latest issue that I need to find time to go and investigate. So. Yeah, could be. So, yep. Hey, Matt, you had a question? Well, I haven't had a chance to investigate that yet. As I said, I imagine it is just dirt on the panels, pollen and dust. But yeah. Oh yeah, no, it. I agree. I have to look into it. It's possible it's an equipment issue. It's possible it's a shading issue with trees. Well, yes, it certainly is likely, aside from the fact that I don't have overhanging trees of my roof. So it's interesting. I have to investigate that. I mean, when I saw that dip in the curve, when I was preparing these charts and pulled out those particular graphs, I went out there and looking at the panels and saying, I don't see any shade. So, yeah, I have to figure that out. So. No, I don't specifically gather weather data. I have a very busy job with IBM, so I have a limited amount of time to spend on this. So, no, I don't gather weather data. I mean, I can tell from a production curve that it was cloudy or it was rainy, right? Some of those earlier curves, way back at the beginning. Right, so this curve here is a day that was cloudy and rain all day. Right, we had a few brief spikes, but this is what a rainy day looks like. Here it was reasonable in the morning, and in the afternoon we started to get some cloud cover. So I don't really need the weather data to tell me that. And as I said, the weather data is 10 kilometers away. So, well, it's good. It's not exactly at my house in terms of cloud cover data, which would be the most interesting, or the hours of sunlight. So.
Have you made any other interesting discoveries?
No, I can't say. Things are actually operating quite well. I guess another kind of interesting discovery is that the efficiency drops with temperature. So I get lower production in the middle of the summer when the sun is higher than I do in April and May. Yeah, the efficiency drops with temperature, and you can, if going back to the picture, the panels at the very top row over this section will have a different performance characteristic than those 4 at the very bottom due to temperature. Even though this array is only 3 panels wide, that temperature difference is significant enough on a sunny day. So, yeah. Sure. Going to page 46. .46 is this. After this? Yeah? Okay. Yep. Okay, so Bluemix is our cloud offering. We have integrated dashDB instances. We have integrated RStudio instances in Bluemix. So when you create a Bluemix account, you say, I want to add dashDB, I want to add RStudio. So we've now added both of these into your environment, and the database connection between RStudio and dashDB is automatically established for you. The required libraries are installed to allow you to create IDA DataFrames within R, and functions are created within dashDB to allow you to do the in-database analytics.
Does it also automatically parallelize as you expand the file footprint?
Does dashDB automatically expand?
Like the R instances that parallelize across the back end as you expand.
Yeah, if you add extra nodes to your cluster, then yes, the parallelism can grow. So, yep.
In the graph that you have, there were like 4 or 5 outliers.
Yes.
Rest of them, are there any R functions that will help you identify only the outliers? What is not wrong?
So in this particular example, I mean, there are various tests you can use to identify outliers. I can see it quite clearly from the residual data. For most of those curves, the data points fitted to the curve will have a small residual in the neighborhood of 30,000. The residual sum of squares will be approximately 30,000. Now these are the reason that sounds high is because of the scale. We're using a second scale, so in the middle of the day, right, you're 20,000 seconds into your day, and your height is 160. So 30,000 is actually relatively small in that scale. For those bad production peaks, I can see the sum of squares residual spike up to a couple 100,000, 1 million. So I can then see. So just that the difference between the good residual and the bad tells me that there is a problem for that day, without needing to specifically pick out, run specific functions to pick it out.
If there was nothing, I mean, in general, if I don't know, visually I can see that.
Yeah.
But is there anything that says, show me only the outliers and leave out the more? Because that's probably what I want to know.
Yeah, I'm sure there are. I couldn't tell you off the top of my head what it is, but yeah, there would be some. I mean, for me, because I've got the 41 residuals for a given day, I can just say, oh, these 35 are all, or these 35 are all, within a couple percent of 30,000, and these other 9, they're 200,000, 500,000, 1 million. Those ones are the ones I need to look at. Okay.
Thanks, Bob.
All right. Well, thank you very much. Thank you for listening to my talk. And I put some business cards on the counter there by the projector. Feel free to take one if you have questions. I'm more than happy to answer them.